Hey everyone. Just pressing record. Okay, good. So I made it to class today. All right, we're going to talk about a different kind of circuit, a different kind of cycle. So last time we were talking about these notions of Eulerian circuits where you were trying to go through every single edge exactly once. And today we're going to talk about a different kind of question. In fact, it's about going through every vertex exactly once. And so at first, if you think about it, it's like all you did is change from going through every edge to every vertex. So it shouldn't be much different, right? I mean, the last one, it was so nice. Last one, we were just like, well, the answer is just about whether or not all the degrees are even and whether or not the graph is connected. Well, now suddenly, we're going to change this to going through every vertex. And you start to wonder, under what conditions could you know that that happens? So that's a general type of question that we want to know. So we want to prove some kind of a theorem. And the theorem is something like, if you have some stuff, then that implies, right? So I'm being clear. It's like there's some stuff. I want to figure out what kind of stuff I can put here. With some stuff, I want to conclude that there's a way to go through every single vertex exactly once. Now that has a name. I'll call it there's a Hamiltonian cycle. Hamiltonian cycle. And Hamiltonian cycle just means it's a cycle, meaning that it doesn't use the same vertex more than once. It's always like something directly adjacent to something, directly adjacent to something, and so on, and you get back to where you start. So a Hamiltonian cycle means that you have each, well, actually, it's just a cycle with all of the vertices. All of the vertices. And that would be a Hamiltonian cycle, right? The point is like, I don't need to say use all the vertices exactly once, because if it's a cycle, I can't use any vertex more than once. And if it's a all the vertices cycle, then it must use every vertex exactly once. All right, can anyone think of any conditions under which a Hamiltonian cycle must exist? Notice that last time with the Eulerian circuits, we were able to make if and only if type statements. We were able to say, well, if all of the degrees are even and it's connected, then I can, get an Eulerian circuit. And now this one is saying, we're not going to be able to say an if and only if, but we just want to find some conditions. Some of them can be pretty obvious. Any ideas of like any condition that you can name so that if I have this, then for sure there is a Hamiltonian circuit, a Hamiltonian cycle? Raise hand. So Nick.
It should be connected.
Oh, okay. So now let's flip it around another way, okay? So I'm going to put another thing right here. Still relevant. What you said is still relevant. We'll go the other way. When I say the other way, what I mean is if there's a Hamiltonian cycle, let's just not say the word if. I'll use implied signs, okay? I'll say there's a Hamiltonian cycle implies, well, it better be connected. Graph is connected. And we did think about both directions when we were doing the Eulerian circuit. So good, thank you for saying this. All right, so there are some things that if there's a Hamiltonian cycle, you better have certain things to be true. And what I'm kind of curious is there anything that we can use to force a Hamiltonian cycle to exist? Braden?
I was thinking along the same line, but one example we could have would be to have a graph that knows and we just like make a circle with the node. That's gonna be making that'll give us a Hamiltonian cycle.
So you're like, if there's a way to arrange the vertices in a cycle and all of them are connected. Yes, this is correct. And yes, that's sort of like, the sad thing about that is it's like, if there's a Hamiltonian cycle, then there's a Hamiltonian cycle. But that's okay. I mean, this is a hard problem. In fact, if anyone finds good ways to decide whether or not there's a Hamiltonian cycle, you might win $1 million. This is related to these kinds of P versus NP, if you can prove or disprove P equals NP, then you get $1 million, which is the smallest part of the prize. Because if you somehow manage to prove they're equal, you can also probably break into lots of things and. But you shouldn't make money that way. Anyway, let's continue and do this. So it's like, yes, we know that if there's a Hamiltonian cycle, there's a Hamiltonian cycle. And the sad thing is, it's actually really hard to write anything non-trivial here. It's really hard. Sean, you were going to say something.
Yeah, so I'm doubting it more and more now that you said that. And I'm not sure if it's related to the first one, but like if each vertex has degrees.
Okay, so I like what you're doing, because what you're doing is you're like, can we find something that would work? Okay? Because everyone here was like, well, here's something dumb I can write. I could say if I have an n vertex graph, all degrees equal to n minus 1, guess what graph that is? That's the complete graph. It's like, duh, there's 1, okay? And I mean, if it's k2, okay, this funny thing of like, what do you do if n equals 2? That's not interesting. So somewhere here, I probably need to say, and n is bigger equal 3, because then you don't have to worry about 2 vertex graphs, but I already know everything there is to know about 2 vertex graphs. There's no theory there, okay? So now this is obvious and stupid. So this is just like not interesting. And what you were wondering is, what if I try to change this? And by the way, I didn't mean it's impossible to write something here. We're just trying to write something here that's like not totally trivial. This thing I wrote is totally trivial. And it will never be an if and only if. The thing I said about the $1 million is if you could write an if and only if for something that's easy to check, well then, that would be rather incredible. But your suggestion is, what about all degrees at least 2? So first of all, you were inspired by that because certainly all degrees better be, I'll write bigger equal to, all degrees bigger equal to, that better be. If there's a Hamiltonian cycle, you got to be able to do that. And now the question is, well, is it true? So let's ask a question. Is this thing true? And that's how I prove it. That's how I think about everything in this graph theory or combinatorics. I'm just like, well, here's a statement. Is it true or is it false? And vertex graph, and at least 3, all degrees bigger or equal to, does that imply there's a Hamiltonian cycle? Okay, Hamiltonian. In some books, you will see people say a graph is Hamiltonian, and that just means it has a Hamiltonian cycle. You might see in some books people say a graph is Eulerian. That means that the graph has an Eulerian circuit. And here this works because otherwise it just runs into my head, so I'm just going to use the word Hamiltonian here. So is it true or not? Well, if we are trying to resolve something true or not, the usual way I deal with it is I first try to say, can I poke holes in it? Can I make a construction of a graph that's not Hamiltonian where all the degrees are at least 2? And if so, then I know it's not enough, but then maybe I try to bolster the fact. So Jack.
I guess to that point, the thing I'm thinking of is like, imagine like a line of vertices connected, and at each end there's like a loop.
Oh, a loop. So we have to be careful. We're not going to loop to our own self, nor are we going to be able to loop to that, because that would make a multiple edge. So that's bad. But do you mean a loop like this?
Right.
Something like that.
I guess I was thinking like maybe some rings at the end.
Oh, yeah. Okay, I get it. So you're like this thing.
Sure.
Yeah, okay. So the problem is you look at that and you're like, oh no, all the degrees are at least 2. That's annoying. So then the problem is it turns out that all degrees at least 2 is not enough because you can kind of break it by doing this. And this is like if you had to go along every vertex exactly once you're going along, you can't go back, right? The Hamiltonian cycle, you have to start somewhere and get back to somewhere. You already see there's more that's here. So what I'm trying to say is, actually this turns out not to be enough, but you're really close. It turns out there's a theorem. When I say you're really close, it's that you can actually do it by just having big enough degrees. So this theorem is by Dirac. Dirac's theorem says that if you have an n vertex graph and at least 3, and all degrees being at least n over 2, that implies it's Hamiltonian. Now this is actually pretty interesting. The fact that just by getting n over 2, I'm good. Because that's like a factor of 2 away from the ideal. The ideal was, sorry, not the ideal. I mean like a factor of 2 away from, I got better in the sense that at least it's not n minus 1. N minus 1 is dumb. That's just a complete graph. This is like a half complete graph. And then suddenly it's Hamiltonian, quite satisfying. Well, whenever we look at this, to understand just how satisfying this is, we also want to show that there are some examples of graphs where you barely don't get the degree condition, and then you also don't get Hamiltonian. That's actually called making this best possible. So it's very satisfying that this is a best possible result, in the sense that it is simply false that if I wrote n over 3, I would get Hamiltonian. So this n over 2 is actually best possible. So I'm going to go to the next screen and say it's also best possible. Oh, let's do a capital B. Best possible in the sense that there are graphs with all degrees. I'll write bigger equal, like n over 2 minus 1. Oops, it's not n over 2, it's smaller than that by a bit, but not Hamiltonian. And here I'm not really focusing on whether n is even or odd. I guess for this you can just choose whichever one you want to draw some graph for. Can anyone think of a way to do this? And that's like really satisfying, because then if I say, well, this is not enough to guarantee Hamiltonian, but you add 1 and it is, that's great. So how could I find a graph to be not Hamiltonian, but somehow all the degrees are at least almost half? Well, now I got to think, like, how would you even go and say I'm staring at a graph and I just know it's not Hamiltonian? I already told you it's going to be really hard to distinguish whether a thing is Hamiltonian or not, unless there's some like really obvious reason why it's not. Braden, what were you going to say?
Yeah, so if we imagine that we have a one point and that we have n minus, or I guess we have nx.
Do you want something like this?
Yeah, where we have like a bunch of vertices on one side, a bunch of nodes on one side, a bunch of nodes on the other side, and they're all connected to this.
Okay, look what happens here. So this is good. What you have here is, this would be, for example, for n odd. And I don't really care too much about odd and even. You can actually also write something for the other case. But this is the n odd case. And if n happens to be odd, I could just break it apart this way. And now this is getting kind of interesting. What are all these degrees? So if you look at the degrees, actually it's even better than this thing. Oh, well, no, it is this thing, because if n is odd and like I take n over 2, that's a half integer. And if someone ever told you, hey, I've got a graph, all the degrees are at least 3.5, you say, aha, then they're all at least 4, because there's no such thing as a half a degree. All right, so that's an important note here. That's why this one's going to look like it's slightly better than that one, but it's really just because of the rounding. If anyone ever told you, I have at least 5.5 friends, then at least they have 6 friends. Okay. So now as we do this, it's like, what happens? Well, all the degrees. So first of all, the guy in the middle, that's got like massive degree. This is like everyone. This person sees everyone, right? This person is friends with all n minus 1 over 2 here, all n minus 1 over 2 there. The degree of this is the full n minus 1. But then anyone else is going to be degree with whatever they've got in their blob. Oh, I should have said, these are like everything. Is that clear? So like each of these is like everyone there and everyone there. And what Braden set up is like, that's a bottleneck. There's no way you could possibly make a Hamiltonian cycle, because you got to go from one blob to the other one and back home. And there's only one thing that connects them. Okay. So now if I do this, what are the degrees? So both sides are the same. So what's the degree of a vertex here? Anyone want to tell me? Suppose I have any vertex in one of the blobs. How much degree does it have? The blob size is n minus 1, and then divide by 2. And inside it's complete, so everyone is with everyone else. Yeah, let's get someone check.
Is it like at most n minus 1 over 2 choose?
Ah, okay, so that's a question, right? So you're like, is that like, so there's a question of what we're counting, right? So the point is like the number of edges. The number of edges is actually n minus 1 over 2, choose 2. That's how many edges are here. But if my question is, you know, I'm supposed to make a statement saying there are graphs where all the degrees are at least this amount and there's no Hamiltonian cycle, then the question I'm asking is, suppose I'm looking at one vertex here. What is its degree? How many direct connections does it have? So it's not going to have a choose. We're not going to need the choose. It is going to have something to do with n minus 1 over 2. Actually, it is n minus 1 over 2. Okay, so I mean, I was going to say you have to minus 1, right? Because it's like if I'm here, and who am I adjacent to? Everyone else in my lump, and my lump is n minus 1 over 2, so this is everyone else in my lump. My blob. right? But now there's also this other guy. Remember, this other guy in the middle is adjacent to everyone. Oh, Abby, you have a question. Or maybe an answer. Yes, and then plus 1. Good, good. So then, good, you were going to give us the answer. You're going to plus 1. Don't forget to plus the 1 because the guy in the middle is adjacent to everyone. So this is the middle vertex. Okay? And so that's just the same simple n minus 1 and then over 2, which, by the way, is actually at least n over 2 and then minus 1. It sure is, right? Because n over 2 and then minus 1, that's n minus 2 over 2. So this is giving you an explicit example of how there are graphs where the degrees are at least, just barely short of half and no Hamiltonian cycle. Actually, well, since I talked about even and odd, why not? Let's go and say, if I had an even number of vertices, I can have another way of making it so that it's not Hamiltonian. One way to make it not Hamiltonian with an odd number of vertices is to have these two blobs and you have this bottleneck thing that you have to get through. There's an even easier way to make even number of vertices into something with no Hamiltonian cycle. Any ideas? And of course, we need like an obvious reason why you just can't get around. Yeah, Braden, you're the construction guy. I mean, coming up with these constructions.
Now we don't even need the bottleneck.
Forget the bottleneck.
Two separated graphs with n over 2 nodes.
Yep.
Really, there's no cycle.
Yep. It's just not connected. So let's just do n over 2 and n over 2. And this is n even. Right? And if I have this, now I just do everything inside, and like no way, no Hamiltonian cycle, just can't get between them. But now if I look at the degrees, that's really n over 2 and then minus 1. Really just n over 2 and then minus 1. So again, non-Hamiltonian. So this is really, really satisfying. We have found out now that putting a minus 1, not Hamiltonian, not guaranteed to be Hamiltonian. It's possible that there are graphs where all the degrees are only 2 and it is Hamiltonian. But the way this is written is, there are graphs which are not Hamiltonian, which have like pretty big minimum degree. And the important thing about the Dirac theorem is, well, if I have a guaranteed degrees all at least n over 2, no matter what, it's Hamiltonian. So now let's go there. That's actually one of the first hard proofs in a graph theory class, where hard doesn't mean it's hard to understand. Hard means it's hard to come up with. In fact, it's relatively easy to understand. So now we're going to, again, remember the Dirac's theorem, which I often say is like all degrees at least n over 2 implies Hamiltonian. You may notice I got kind of lazy and I didn't write n at least 3 because actually at this point, the way it's written, I'm also guaranteed that n is at least 3. The reason is because if n equals 1 and I have a graph where all degrees are at least 1/2 and there's one vertex, there's actually no such graph. You can't do it. And the way mathematical logic works is like if I say, the following statement is true mathematically. If 0 equals 1, then 50 million equals 4. That's a true statement because the original part is just not satisfied, right? You can always say if false, then false. That's legit. And so here it's like if I say all degrees are at least n over 2, well, at this point, I can't even have n equals 2. Because if n equals 2, I need to have, oh no, I can. Okay, I need n at least 3. All right, so I was going to say this thing, if I put n equals 2, then I would say there's no such way to make all degrees at least 1 and 2 vertices. Well, there is. That's just called 2 vertices and 1 edge, and that's not Hamiltonian. Sorry, guys, I need to say n equals 3. And at least 3. And at least 3. Okay, now it's a true statement. As you can see, I always get caught under like very small values, but that's because most people don't care about the graphs which have just a few vertices. All right, now let's try to prove this. Well, in order to prove this, I'm first going to say the hard part about it is that you somehow get to go to all of the vertices. And something that's also quite shocking about this is like, remember that we broke Hamiltonian just by making it disconnected? Well, what this means, by the way, is that if I have n at least 3 and all degrees at least n over 2, somehow that's going to let us prove the whole graph is connected. Because if I can't prove connected, that means that there's some graph that's not connected, and that's definitely not Hamiltonian. Okay, but to move along this direction, the first thing I'm going to do is I'm going to say the hard part is actually getting the Hamiltonian. The easy part is getting a cycle, which might not be the whole length. Okay, so let's start easier. N at least 3, all degrees at least n over 2 implies there's a cycle with, I'm going to say at least about n over 2 vertices. You can actually do a little bit better than this, but this will be enough for me to say I can get halfway there. How does this work? And I also need n at least 3. So how would this work? Actually, this looks awfully like a homework problem. If you guys have been thinking about the homework that's due, I think, next Friday, there's some problem on it. And it looks a lot like this one, actually, what I've just written here. That somehow if I have all degrees at least something, then there's a cycle of at least that many vertices-ish. And the way this one works, like this particular proof works, is you say, let's just start walking. You just like walk. You have all degrees at least n over 2, which, by the way, if I combine both n at least 3 and at least n over 2, that means that all degrees are at least 3 over 2. So all degrees are at least 1.5. Remember, degrees are integers. So that implies that all degrees are at least 2, right? Why is that useful? Well, that lets me know I can start walking. So let's start walking. Any vertex. And I can just always walk because all the degrees are at least 2. If I can go in, I can always go out since the degrees are at least 2. And I just kind of go and go and go and go. We've seen this argument before. We've seen this kind of argument before. And what we found out is that at some point, like the game Snake, you crash into yourself. Oh, I should probably have said something here about, n is a number. It's a finite graph. Because otherwise I have like nonsense. It's like, what does it mean all degrees are at least infinity over 2? So I mean, like, I should actually emphasize, in this class, all graphs are simple, meaning there's no loops from vertex to vertex. There's no multiple edges. There's no two vertices with like many edges between them. And also all the graphs are finite. So now, so far I got this thing. I got a cycle. But I'm not happy yet. That's just a cycle. I need a cycle with at least n over 2 vertices. So now how do I go and say, I'm not sufficiently happy with this cycle. I want to know the cycle is big enough. Well, the key is I have some choices. So far, when I made the cycle, all I said is that, every vertex, you have at least degree 2. But actually, it's not just at least 2. It's at least n over 2. So for example, whenever you're looking from the point of view of here, this cycle looks too short. This is like 5. And n over 2, oh no. It's not too short. It is n over 2. Okay. Just kidding. There's more graph. There's more graph around. See? More graph. Lots more graph. So now that's really just too short. So I just made more graph. I'm just trying to say like that. I don't want to declare victory with that. That cycle was too short. Okay? And by the way, this particular picture, this is not the whole graph because every vertex's degree has to be at least n over 2. And so far I only drew like 2 degree. So importantly, there's like more choices. And since there are more choices, surely you could choose a better choice. That's the idea. It's like, don't cut yourself short is sort of the feeling. But how do we make that rigorous, right? So now there's an idea here which is like, don't cut yourself short. Use choices. Okay? But now I want to give like some slick way that you can handle this. So a standard way would just be to say, just take choices, and so on. A more slick way to do it would be to say, let's suppose that I already took the very longest path that I could find. And this is an example of what's called an extremal argument. It's where you say, I'm trying to prove something, and let's just say I'm already staring at the biggest of something. And I'll make some deductions based on that. Okay? So what we're going to do here for this starting easier thing that we're proving, so we're going to prove the easier thing. Proof of easier thing. A very powerful tool is to say, suppose I have this graph. I went and I already did all the hard work to find the longest path. Found the longest path in the graph. Here it is. I draw a long path by simply drawing a line and then putting the vertices on. That is the longest path in the entire graph. Of course, by the way, there's more graph around, and I just it's not like I'm saying I draw this first and then draw the whole graph around it. I'm saying you're just staring at a graph, you did all the hard work. Here is the very longest path. Remember, path means I can't use the same vertex twice. That's an important point here. Remember, path can't use the same vertex twice. Okay, so now I've got this. Are there any interesting conclusions if I happen to have a longest path? What does longest mean? Well, I got stuff sticking up. I mean, I've got stuff I can go to. Can anyone tell me anything about what has to happen here? Remember, all the degrees are at least n over 2. In particular, the last vertex has a degree at least n over 2. Nancy, anything you can say about this last vertex? You can't continue, right? So that's what you're saying. I'll use the blue to emphasize here. It's the longest path. So these things can't go to new vertices. These things have to all come back to the path somehow. They can't go to new vertices. Or else it's not the longest path. Else it's not longest. That's the power of using something which is like a longest or a shortest or something. Oh, so they have to repeat vertices. Okay, so it has to go back. So it's like this. Or something. All right. Can anyone tell me why there's a pretty long cycle then? Pretty long meaning I'm supposed to find a cycle which is at least like about n over 2-ish number of vertices. Why does the fact that from this guy I'm supposed to have, since I have all degrees at least n over 2, why do I have like a pretty long cycle? Nancy again.
So it has one edge from an existing from this one.
Yep.
And also n over 2 minus 1 other edges that has this.
Yep.
So we count with the number of edges, I think plus 1, and that's the number of vertices in the cycle.
Okay, I think the important thing that you were doing is you want to go all the way back to the first one, or the farthest one. Is that what you're trying to do? So I think the key idea here was, from there, just go all the way back to the farthest one. And because of the fact that there's supposed to be n over 2 things coming out of here, you're guaranteed that the farthest back is going to actually be at least like n over 2, in fact, plus 1. Well, there's like at least n over 2 other things besides yourself inside this picture. That's the easiest way to think of it, actually. So you have yourself here, and you are adjacent to somebody, and each of these other things that are coming out are adjacent to different people, different vertices. So actually, you're here, and out of all this other stuff in my highlighted yellow path, there's going to be at least n over 2 things there, distinct vertices. So that's how you know that this entire cycle has at least n over 2, in fact, plus 1 vertices inside it. So the way I'll say this is that inside here, I have at least n over 2 vertices here. And the here is this part, right? Ooh. I should not have drawn it all the way to the current one. Here, to the last one. Here. Like this. And then there's this extra one over here. So I get n over 2 plus 1, in fact. And it's even better. So that's the proof of the easier thing. Now, the problem is that that's not what we wanted. We wanted 2n over 2. We wanted to double this. But it turns out that this idea of the longest path ends up being really useful. But now I'm going to pull back to another point on this Dirac theorem. It's like, wait a second, how did we even know that the graph was connected? We're actually going to need that fact in order to finish this. So going back to Dirac's theorem, so back to Dirac. Let's start by, we're going to prove now. So I should write PF in front. Okay, so let's prove the entire Dirac's theorem. Let's start by showing why it's connected. I need to say that if n, I don't need the n at least 3 here. I just need that if all degrees are at least n over 2, that's going to imply it's connected. Okay? Now, when I said I don't need the n at least 3, remember Dirac's theorem lets me use n at least 3 if I want. And I will need it at some point to finish the whole thing. But for this part, I'll just say, actually, if all the degrees are at least n over 2, I'm already happy. I got that the graph, I mean, I'm going to prove that the graph is connected. And when I was thinking about it, it's like, yeah, even if n equals 2, then all the degrees are at least 1. That means it's just this, and it's connected. So even the small cases are not a problem. But now, how would you do this? So the way you do this is it's easiest to think about this like proof by contradiction, and that's actually going to introduce this notion, or bring in this notion that we talked about before, of connected components. So why? Let's use green, because then I can use a different color for the next piece. So why, suppose, not connected? If it's not connected, we had learned before that you can just take the graph with n vertices, and you can think of how it separates into these connected components. Separate the vertices by their connected components. So, you know, I have some blobs of connected stuff. Writing some blobs. So I've got some blobs. These are all connected to each other. Each of them is individually connected. Randomly drawing some stuff. Okay. Can anyone help me get a contradiction now? I'm saying suppose I have not connected. I have separated into their connected components, and I get at least 2 of them. At least 2 components. Is there a good reason why now I contradict the fact that all the degrees are at least n over 2? Could I have at least 2 different components, possibly 3, possibly 50, so that every single vertex has degree at least n over 2? Ah, another person, new person. Andrew. Good. So what you just emphasized is that, hang on a second, how in the world are you planning to have such big degrees if once you got 2 components, somehow if they were equally split, each one doesn't even get to n over 2 degree because you can only be adjacent to everyone except you in your component. That's your philosophy. To tighten it up a little bit, the only question is like, well, what if they're not evenly split? Then the way you do it is you just say, if I want to break the condition all degrees at least n over 2, I just need to find me one vertex whose degree is too small. Where should I go hunting? Which component? The smallest one. Okay, so that's like how you like argue this thing, right? If not all the components are the same size, well, focus on the smallest component, the smallest number of vertices. Focus on component with fewest vertices. Well, now I've focused on this thing with the fewest vertices, and the question becomes, in that case, what do the degrees look like? Well, the component with the fewest vertices, the number of vertices is at most n over 2. The reason it's at most n over 2 is just because, well, as soon as I have 2 components, one of them is less than half. If I had 50 components, one of them is less than n over 50, which is really less than n over 2. So definitely I have this as true. And now you just look at it and you're like, well, unfortunately, the biggest degree in there is at most n over 2 minus 1. Biggest degree there is at most its size its number of vertices, minus 1, which is at most n over 2 minus 1, contradiction. Because we said all degrees at least n over 2. So that's very satisfying. We now have gotten that it happens to be connected. Now for the second part of this is where there suddenly is a leap. And that's why this is a difficult theorem to come up with, to invent on your own. But it's amazing once you look at it. The second thing is, hey, let's just look at the longest path and see if we can find anything interesting. Which is funny, because we were talking about finding a cycle, right? And suddenly I'm saying, let's look at a path instead of a cycle. You might say, if I want to go and find a Hamiltonian cycle, let's look at the longest cycle. But the answer is no, don't look at the longest cycle. Look at the longest path in this entire graph. So second step is look at the longest path. Well, that's going to be long path. Okay. Now if I have this really long path, I want to say there's a problem if it doesn't have everything. Okay? So I'm going to give the reason I say this is hard to come up with is that I'm going to tell you what is going to happen. We're going to take this longest path, and what we're going to show is we're going to show that there exists a cycle which has at least this many vertices. That's our goal. We'll show there's a cycle with at least this many vertices. Now, why is that obvious that that's what I care about? That's not obvious yet. But the claim is that's why we did the step 1. Okay? So first of all, we're going to say if there's this longest path, we'll show there's this cycle with at least this many vertices. Who cares? I always like to answer the who cares, and then we can go and prove this statement about this particular path. Why would we care? So the step 3 is going to be, I guess I shouldn't have drawn the path. I'll have to draw it again. I'll have to draw it again on another screen, because I'm going to write the who cares first, and then we'll focus on the yellow part. Who cares? Well, longest path gives me a cycle. Can anyone think of a situation in which you would then be done? So remember, let's suppose I got 1 and 2. Suppose 1 and 2 are both true, which means if there's a longest path, then there's always a cycle with at least this many vertices. Can you tell me any situation under which, like, if I'm staring at this longest path, then I'm like, bingo, I'm done? Braden.
The longest path has to include all the nodes, then we're done.
Yeah. So first of all, if it has all the nodes, if it has all the vertices, bang, we're done with step 2. Okay? That would be great. So I've got 2 possibilities. If the longest path has n vertices, n is the number of vertices. I'll just use the word all n vertices, then 2 gives Hamiltonian cycle. So that's like the easy case. That seems nice. Else, now what? Suppose I don't have that much luck. So instead, I got a longest path that doesn't have all the vertices. Else, the longest path is missing at least one vertex. Okay, let's try using 2. So first I use 2. So I'm going to walk through this because this is non-obvious. But like, okay, if it's missing at least one vertex, let's use step 2. And I will get a cycle with at least that many vertices. 2 gives a cycle with at least that many vertices. Okay. Under one condition, I'm already happy. If that cycle happens to be all the vertices, I'm like, I'm done. Actually, now that I'm looking at this, I'm like, I could probably have done that before, because no matter what, whether I happen to have the longest path with n vertices or not, I'm going to use the step 2, right? So no matter what I'm going to use step 2, I'm going to stare at some kind of a cycle. If already all n vertices, you're done. Else. Now here's where it gets interesting. Else. So now I have a cycle somehow. There's a big old cycle here, and it looks like this. But it's not all the vertices. It's missing some. How can I get a contradiction? We haven't used step 1 yet. So we have to use step 1 somehow. I have this long cycle, and it's missing some stuff. Missing vertices. What now? I'm trying to give some time because it's these kinds of things, like if people have a chance to think a bit, then suddenly it's easier to keep in your head. It's like I have this cycle, it's not going through everything. I would love to get some kind of contradiction. The kind of contradiction I got before was about, oh, then it's not the longest path anymore, which is what we want to get to, right? So we're staring at the cycle, it's missing some stuff, so there's like some stuff out here. Step 1 says you're connected. How could I try to use that to contradict the fact that I had the longest path before? Well, by finding a longer path. Ah, Nancy. Okay, so I'm hearing this, like you want to take apart the cycle. That's the way to go. The key, let's just like make it a little bit, I'll help you crystallize that a bit more. You're right, it's something to do with taking apart the cycle. The key is, hey, the graph is connected, right? So if the graph is supposed to be connected, what color was that? That was green. So since it was supposed to be connected, well, there's some way to get out into missing land. Does that make sense? Like you gotta be able to get to the missing land somehow because the graph is connected. So this thing is from 1. But now, that's what you do. Now you just go and you take apart the cycle. I should have drawn something which is easier to highlight. Go all the way around to there. I'm not sure if you can see what I highlighted. I basically said, take that little step that goes out and then go back into the cycle and go around the whole cycle and just stop right at the very end. What you should see here is that you just got 1 more vertex. And that was probably what Raiden wanted to say, but I wanted to let more people get involved in this, right? It's like you got 1 more vertex than you had before. It makes sense. It's like if I've got this cycle and I got some stub sticking out, then I can just go and pick that stub, that vertex, and then use all the vertices of the cycle too. So in this case, what I've gotten is I've gotten a longer path. Because I started with a path, I made a cycle which is at least as long, and then I got a path which is even longer. Contradiction. This contradicts longest path. So this got longer path. Oops. Contradiction. Okay. Well, in that case, now I know why I care, right? Like this magic of if I've got a path, I can get a cycle. As long as I can do that, then I sort of just use that and I finish. Okay, so that leaves the last part, which is how do I get this cycle? And this is actually why this proof is like not trivial. It's like, how would you think of doing something this way? Well, now let's stare at this longest path, okay? The only thing left is if n at least 3, all degrees at least n over 2, then given a longest path, there is a cycle with at least as many edges, as many vertices. At least as many vertices. I actually want to draw it more in the middle because I'm going to do something to this picture which involves both the top and the bottom of it. Okay, so now that I've got this longest path, let's go and start to think about what we knew before. Like before we knew something about the longest path, which is that all of the neighbors have to go back onto the path. Right? They all have to go back onto the path somehow. And remember that this degree is at least n over 2. On the other side, I also have that all of them go back somehow. Blue. All of these are degree at least n over 2. And I have it on both sides because it's longest. So if I could like extend myself from the beginning, well, then I also got a longer path. Now, how could you use this kind of a picture to get a cycle? My goal is to get at least this many vertices. So I would like to find a way to be like, well, you know, if the stars align, I could make a cycle that uses all the vertices I see here. All the vertices I see here are the vertices of this path. Like one way to do it is if the beginning and the end touched. Like if there was just one edge from the beginning to the end, I'd be like, hooray, I'm done. I got my cycle. But you're not that lucky. And it turns out there's another way to get a cycle. Can anyone see a way that if you were so lucky, you would get a cycle using all of these vertices? Jack.
It'd be nice if there's like some blue edge, I guess, the way you've drawn it, that goes like in front of where one of the green edges there, right?
Yes.
One behind.
Yes. So this thing. So this is actually why this is a hard proof. It's like, oh, look at that. If that happens. So this is like cool. So if that happened, then you could do this. You could go and make this cycle. The first time I ever saw this proof, I was a college student, and I was like, that is just like too slick. This was in my combinatorics class. I was like, who would think of that? Well, obviously Dirac. But anyway, so it's like this particular thing is that if you just happen to do that and go one ahead of the other one, you're good. The reason why this is non-trivial is because sometimes you're like, hey, what if they both hit the same one? Well, that's useless. If the blue and the green hit the same thing, that's a figure 8. Which is not going to give you a Hamiltonian cycle because you're supposed to use every vertex once. The magic of this is that it used every vertex once, and you didn't have to use the same vertex twice. So that would be cool. How do I prove that that happens? So now I know that the entire goal is to show that happens. Goal: show this happens. To do that, I'm going to go into the next screen, just because I don't want to mess up this picture. Let's go to the next screen and start to be like, well, assume it doesn't happen. Assume it doesn't happen. Well, in that case, I have my path. Okay. Maybe let's draw where the green things go. The green things go somewhere, okay? So the green things, I've got some green things. But now what I'm going to do is I'm going to draw some x's, which are called like off limits, right? The blue is not allowed to go there. What I'm going to do is for every green thing, I'm going to draw an x right above the vertex that's just to the right of it, because I'm assuming it doesn't happen. So if I'm assuming it doesn't happen, then there are some places which are not allowed for blue to touch, right? You'll get x's blocking where blue can go. And because of what you just said, I'm going to draw the x's always one to the right of wherever the green landed. Actually, just for completeness, it turns out I can even think of the very last edge as a green edge. Does that make sense? And here's why. If I think of the very last edge as a green edge, and I use the same rule of saying, well, let's go one to the right and put an x, why is it like logical also to say that that last vertex is off limits for blue to hit? That's not because of this fancy figure 8 switcheroo-ish thing. That's for a really dumb reason. Why should I mark that one off limits for blue anyway? Braden.
Well, if you have the left side going to the right side, then you just immediately have a cycle.
Boom. That's the whole cycle, right? So that's satisfying. Okay, wait. How many x's did I draw? I drew at least n over 2 x's. That's why I used the fact where I said I'm even going to think of that last edge, because for every single degree of the rightmost vertex, I got an x. Okay? So I get at least n over 2 x's. because every single degree of the green, including the guy that they were directly adjacent to, gave me an x. Now blue is supposed to make n over 2 connections. Blue needs n over 2 landing points. But look at where blue is supposed to go. So blue, by the way, one of the ending points is here. Okay? That's fine. So blue has all of these ending points. Blue has all these ending points. This is actually one of them. I already know that's an ending point because that just happens to be where it is. Blue has all these ending points. And what I'm going to do is I'm going to draw a blue box. Inside this blue box, blue lands at least n over 2 vertices here. Now, why is that a contradiction? This is now good shape. I have somehow some off-limits things. I have at least n over 2 off-limits things. Blue is supposed to make at least n over 2 landing points. Landing points aren't allowed to go on off-limits. I want a contradiction. My contradiction should be that there's no way I can fit everything. Brandon. Good. So there was one important thing. Just a second. There's an airplane overhead, so I can't quite hear. But you said something about box has at most. Yes, at most n minus 1 vertices in the landing box. Because notice, it's like, I said at most n minus 1, because I'm just saying, suppose I had the longest path. I don't yet know that the longest path is of length n vertices. But no matter what, it's missing one. The landing box is missing one. So now it's just not going to fit, okay? I have n minus 1 space. I'm supposed to have n over 2 blocked, and I'm supposed to grab n over 2 other ones. It doesn't fit. It's a pigeonhole principle. Actually, that's the insight for why there's an n over 2 in this entire proof. The reason why we got an n over 2 is we managed to pigeonhole from the two ends, my left, right is all mixed up. Anyway, the two ends, the two ends coming in. Right, so we managed to pigeonhole from these two things coming in, and they're not allowed to hit the same thing. So that's it, it's over. So what we just found out is not enough space for at least, let's use colors, for at least n over 2 x's and at least n over 2 landing points. And the not enough space is n at most n minus 1 vertices. That's it. Contradiction. And that's the entire proof of this Dirac's theorem. All that happened here is we just used the idea somehow that from longest path, you got cycle. And then what happened in this proof effectively is like, well, if I had the longest path and it was everything, done. If it wasn't everything, I'm just going to go back one step to recap. If it wasn't everything, 2 steps to recap. If it wasn't everything, then somehow you'd be able to get a cycle out of it. If that wasn't everything, it's supposed to be connected because of what we proved in the first step, which lets you get a longer path, contradiction. So that's this proof. And I mean, this is one of the first non-trivial proofs. You may notice some relation between this and your homework, and that's because the goal was to let everyone get familiar with this idea too. And that's it for today.